Most of you guys are Maddie, right? Materials, about 80% of the class. Does anyone know what a Prince Rupert's drop is? No? Okay. So before we start talking about residual stress in welding, I've got a quick video for you guys. Oh, and we don't have any audio, but we've got closed captioning. So what they're doing here is they're taking molten glass, same sort of glass you'd have in a car windshield, just plain old, I think they said it was sodium glass, and then they're putting it in ice water. Now as it goes into the ice water, it forms this kind of tadpole shape. And the outside of the drop is cooling first and locking in its shape. And the inside is still molten, so it's okay, it doesn't mind the shrinkage of the external shell. But then as it continues to cool, the inside cools and it actually pulls on that outer shell, putting the outside of the drop into compression, and the inside is resisted from shrinking, so it goes into tension. So you end up with this weird structure of compression around the outside and tension in the core. Now they're going to then take this drop and they're going to hit it with a hammer. So what do you guys think is going to happen?
It's going to shatter.
It's going to shatter?
Actually, nothing's enough.
So we got nothing and it's going to shatter. Anyone else? Those are kind of our two options. So let's see if they... So this is a big hammer they got set up. I think it's, a couple pounds of steel. They're going to drop it. It's going to swing down. Nothing. Now, what do you guys think would happen if that was a typical glass? Didn't have this kind of weird structure? Probably explode. Pretty much everyone here has probably dropped their cell phone, lands at just the wrong angle, and your screen shatters immediately. But this structure of having compression around the outside and tension in the inside, now what they're going to do is they're going to take the tail of that drop and they're going to cut it with pliers. Completely shatters. So the reason that's happening, if this will now load, is residual stresses. So when you have that sort of structure where the object as a whole is in equilibrium, but parts of it are in compression and parts of it are in tension, it's typically a result of residual stresses. Now in welding this happens because when you weld down the middle of your part, if you're joining two plates, the area you've welded went to very high temperatures, melting, and is cooled back down. The area far away typically hasn't reached nearly the same temperature as your weld. And so you have a thermal stress that develops while you're welding. Now, most people here weren't mechanical engineers, so you wouldn't have heard of Timoshenko, but this is kind of the first book on the theory of elasticity, principles of materials. And so I went to their book and I pulled the definition of thermal stress. And they say that thermal stress is, the cause of initial stress in a body is non-uniform heating. So in welding, typically we have non-uniform heating. We're not getting our entire object to the same temperature at the same time. There's always going to be some amount of non-uniform heating. And such an expansion generally cannot proceed freely. So those are kind of the two elements necessary to develop our residual stresses. We have heating, which is non-uniform. Some parts of the object want to heat up at a faster rate than others. And whether it's because of the geometry where you're restraining this, you're clamping something down, or just the fact that you have parts that are hot while other parts are cold and they're joined together, that expansion that wants to result from that heating is constrained. So typically in welding, if you're welding along a plate, you end up with something like this for your temperature field. So this is something we talked about back when we looked at temperature in welding. If you weld and you imagine that you're moving up along the plate, so you're welding from the bottom to the top, then your heat is going to follow your, I got a pointer here, perfect. If you're moving from here, this would be where your weld heat source is right now. And this is the temperature field that's flowing away from your heat source. So right at the tip of your heat source is where your maximum temperature is going to be. So I've cut this here at 300 degrees. You can imagine at the point of your heat source, you're way, way hotter than 300 degrees. You're up near melting temperature. But as you move both further away behind the weld and across the plate, your temperature decreases. Now one thing you notice here is the temperature field in this direction is completely different than in this direction. And this is typical for kind of the fast-moving heat sources we have in welding, where typically your thermal gradients are going to be really, really huge across the plate and comparatively small in this direction. So that means as each element of the plate wants to expand, the elements next to it are going to be expanding at a different rate, they're going to be at a different temperature, and they're going to be stopping those elements from expanding. And what you see is resulting from this is in this region where you have really high thermal gradients, you get high stresses. And this is typical of what you'd see for stress development while you're welding. So the entire class now from this point we're going to be talking about how we understand what's going on, how we relate the temperatures and the thermal stresses to then the residual stresses that result from welding. So typically when you talk about residual stresses, you also end up talking about distortion. These concepts are not necessarily exactly the same, but they tend to be related. Sometimes if you look in books, you'll see people who write a diagram where they have residual stress high, distortion low, and as distortion gets higher, residual stress gets lower. And I would say that's not technically true. But what they're suggesting is if you have residual stresses in an object, typically it's because your object is extremely highly constrained, like we talked about. If you want to heat it and it can't expand, then you develop stresses of that restricted expansion. Same thing with that drop. As the outside is cooler than the inside, when it wants to shrink, it can't because the outside is holding it, so you end up with stresses that develop because of that. Now, if you have something that's not freely, or it's not completely constrained, it's free to move, typically then you have different parts that are expanding and contracting at different rates. Parts get locked in during welding where they end up being solid, parts still expand after, you end up with distortion. Now, in this case, we're going to talk about welding stress and distortion kind of at the same time. And it's true that in some cases, you might have high distortion and low stress, or high stress and low distortion. But the reality is typically somewhere in between. You're never going to have no distortion when you weld, unless you really, really clamp your part so it can't move at all. And you're typically never going to have no stress either. The reality is as you develop some amount of stress, your part's going to deform a little bit, distort, to try to redistribute that stress in the lowest stress state it can achieve, and you're going to have some distortion. And if you clamp it in some way, you might have more stress in one part because you've restricted it so it can't move. But if you let it freely contract or freely, oh, I'm not sure what I got here. I'm going to have to keep talking. Apparently the class in front of us overheated the projector, so.
Or maybe they didn't put enough time. It just ended out.
It says it's just cooling off, but. So, I'll draw up here what we had on the slide there. So if you imagine a T-joint here, and you put a weld here, then there's a couple different ways in which having stresses in this weld could affect the geometry of this part. If you think of the stresses across the weld as this wants to shrink in, it's actually going to end up pulling on this part, and this is going to bow up, and that would give you angular distortion. The same thing can happen if you have a plate like this, where your weld geometry changes as you go up. You have more material at the top and less material at the bottom, which means that as this shrinks, this is going to want to shrink more than the lower part, and you get that same thing. The plate is going to bow up. Those are both what we call transverse distortions, or caused by transverse stresses. That's stresses across the weld. The other option is you have stresses in the direction of welding. So typically, the coordinate system we use for welding, if you imagine you've got a plate here and you weld down the middle, this direction we're going to call the transverse direction, or the y direction if you're using the system of coordinates we use for heat transfer, or y is across the weld, and x is in the direction of welding. And this direction we're going to call the longitudinal direction. For transverse stresses, they're typically determined by the restraint of your material. If you think of these plates and you imagine you weld relatively fast, this whole weld's going to be hot at the same time, or close to the same time. And if this plate is free to expand and contract, you're not going to have huge stresses across the weld. The whole plate's going to want to get a little bit bigger, and it's not going to be restricted much at the edges. And then the whole plate's going to want to get a little bit smaller. Same thing you can imagine if you're welding a really big pipe. When you weld two pipes together.
But the computer again.
Oh, they're perfect. So if you imagine you're welding two pipes together, actually that's a diagram I don't have up here, and you've got really long lengths of pipe, there's not a lot of restraint there. The pipes can actually kind of act like two big springs, where your stress across the weld is not going to be as significant as your stress in the direction of welding. So the longitudinal shrinkage, which is what we're going to spend most of class talking about, is that stress in the direction of welding. And typically, that's going to be the stress that causes the most issues in pipeline welding, and in a lot of cases, it's going to be the stress that causes the most distortion that you're worried about. So I mentioned this a little bit on the board, but I'll go through it here. Transverse stresses are driven by the thermal shrinkage of your weld. One of the misconceptions about transverse stresses is that it's just the weld metal shrinking. You have hot weld metal, it's like you poured that hot weld metal in there, it cools off, and it shrinks. In reality, that's not nearly enough to account for the thermal stresses and the thermal shrinkage you see in the transverse direction. What happens is if you have something restrained and you heat it, those plates are actually going to get bigger as you heat them. And that actually closes up the gap and compresses that metal while it's very hot in the weld and doesn't have a capacity to handle that stress. And then it locks itself in that closed position. And as it shrinks, it's now pulling back to return to its original shape. So it's not just the weld metal that's shrinking because you had molten metal, it's the surrounding material that got heated up to the point that it expanded into that gap, and now it's returning to its original shape. So transverse stresses depend highly on the restraint. And in a multi-pass weld, it's not just the restraint of your plate, but it's the restraint of the earlier passes. So if you look at the case we had here, where we have a first pass, say a root pass, that gets put in here. Now for each subsequent pass, when that wants to expand and pull back together, this pass is restraining it. So as we move up, each of these passes gets more highly restrained, and the stresses are not then consistent throughout the thickness. And an uneven stress distribution through the thickness is what gives us those distortions. And typically this can be a real big concern if you have high restraint, because as you imagine that as you get to the outside, you actually start to maybe bend across the root. And bending across a root is typically very, very bad in welding. You put high tension stresses across the root, and if you have a little bit of a notch here, just from the geometry of when you're actually putting that pass in, if you're going from the outside, if it's a pipe, you don't have access to the inside, you might not have a perfect geometry. Now you're bending across that imperfect geometry, and it's the worst case scenario for forming cracks or other defects. So it's a big concern. So if you look at the effect of different joint prep, you can imagine that some joints are actually going to be more desirable for reducing that angular distortion than others. If you have a standard 60-degree bevel and you're only welding from one side, each pass you create is going to produce more and more angular distortion. In comparison, if you have a 60-degree bevel where you split from both sides, now if you weld from one side, you get some distortion, some stress, but you flip it and you weld from the other side, you're reducing some of that distortion. You're kind of bringing it back into its original shape. Now that doesn't necessarily mean you're reducing those stresses, because you're still now having restrained material, whereas you put those additional passes in, the first passes are now actually going to be stressed back the other direction. But the overall distortion, angular distortion, should be reduced. And this is why it's not always true to say that less distortion means less stress, but a lot of people, if you look at just a case like this, as you can imagine, you're reducing distortion, but you might be increasing your stresses. But that's very specific to the transverse case. As we look at the longitudinal case, we'll see that rule doesn't always apply. Similar idea, but now looking at a whole bunch of different bevels. You can see that it's not just the angle of the bevel in the double-sided versus single-sided, but as you compare these different geometries, more metal is also going to make a difference. So if you look at 60, 90, and 120, all three of those are the same one-sided weld. But as you get more volume of weld, what we learned, I think, 3 classes ago when we actually did calculation, if you look at the deposition, you can draw a relationship between deposition and heat input, which is roughly about 60 joules per millimeter of length per millimeter squared of weld deposit, or 60 joules per millimeter cubed. So as you have to deposit more material, you're putting more heat in. Now, it depends on how you put that heat in and exactly what your stress are going to be. In this case, this is just kind of a schematic diagram, but you can imagine there's going to be a big difference if you deposit this entire pass, or this entire weld in a single pass with all that heat together, than if you put a little bit of heat in for one pass, a little bit heat in for the next pass, and just adding little bits of heat at a time. So this is just a comparison of the different geometries. from kind of a transverse perspective. But in a longitudinal perspective, which is what we're going to talk about from here on, it's not so much just about the volume of metal, but how much heat you put in and how you put that heat in. Typically for distortion, one of the principles for longitudinal distortion is that the less heat you put in, the more passes you use to fill a certain volume of metal, the less distortion you're going to have, the less stresses you're going to develop. So from this point on, everything we talk about is going to be related to longitudinal distortion. So before we stop talking about transverse distortion, does anyone have any questions? Awesome. So longitudinal stresses are typically something anyone's familiar with if you've dealt with 3D printing. Has anyone here went to the garage and 3D printed something? A few people. Has anyone had a print that lifts off the table, peels up, and you go to recover it and it doesn't look the same shape that you expect it to look? It's happened to me. I'm sure it's happened to at least one person here. And what's happening is as you put subsequent layers on top of the earlier layers, they develop longitudinal stresses. And one of the ways they try to reduce the effect of those stresses is to keep the whole print hot. So if you have your build plate for your 3D print, and you're printing something that's building up layer by layer until you end up with this structure where you have walls. If you imagine these are outside walls and a hollow interior, each of these layers is going to have some longitudinal stresses, some shrinkage. Now to minimize those stresses, they minimize how much it can cool. If you imagine you're at a high temperature when you deposit that material, as it cools, it wants to shrink. So this plate is typically heated. Now what happens if you have a little bit of lifting of one corner is now it's no longer in contact with the plate beneath it. So it cools more rapidly in that area. And the whole thing ends up wanting to bend a little bit, and it lifts up a bit more, and it bends a little bit more, and it cools a bit more, and everything gets out of hand until your whole piece ends up looking kind of like a potato chip. And it's all related to residual stresses. And that's one of the reasons people are really interested in residual stresses right now, is people have moved beyond plastic manufacturing with 3D printing to now metal additive manufacturing. I think there's at least a few professors in the department who are now really involved in that. And these sort of dimensional changes can be extremely significant if you're trying to manufacture this complex part of a really difficult to machine alloy where you're using additive manufacturing, because you don't want it to end up with a different shape than you designed. You want to get as close to your final shape as possible. So typically when you look at a longitudinal stress distribution for welding, you end up with something that looks kind of like this, where your weld has heated up in the area near the weld metal, near the fusion zone, and then it cools back down. And you end up with this distribution of tension and compression. Now, I'm telling you that there's tension here and compression here, but hopefully at least a few of you are looking at that and saying, well, that's not enough. Why? So we're going to spend pretty much the next 50 minutes talking about why there's tension here and why there's compression here, and why not compression here, tension here, why not tension, compression, why this distribution. Now, another thing that's important before we get to that distribution is to understand why we're even caring about residual stresses. I showed you guys that video of a Prince Rupert's drop, so hopefully at least some of you believe that in some situations, if you have residual stresses and something goes wrong, it can go really, really wrong. But that was glass. What about for steel? Well, if you have tension here and compression out here, you end up with a situation where in the simplest case, you don't have uniform stresses throughout your part. And so imagine that this was not a plate, this was the top of a beam. Well, you have tension in the middle of your beam, and this compression wraps all the way around the edges of your beam. Now you have an unmatched moment where you have a force on the top of the beam and no matching force on the bottom, because the matching compressive force is distributed around it, and you get bending. If anyone's taken a strength of materials course like Civ 270, and you see that you've got compression here through a large part of your plate, one of the problems when you have compression in something, especially a thin plate, is you can get buckling. And we get the same thing in plates as we get in beams. I think everyone who took Civ 270 buckling is something you remember learning about. And it's all driven by what the magnitude of your compressive stress is. One thing we're going to see a little bit later here is in practical applications, this compressive stress is one of the first reasons people really tried to understand and predict residual stresses in welding. Because if you take a beam that's been welded to make it into its shape, if you imagine you've got a hollow structural section. So a hollow structural section is kind of a typical term for anything that's got a hollow tube, whether it's square, rectangular, that's used in structural construction. So typically you imagine you have a section like this, where you have some wall thickness around the edge, and a long length of beam. And beams like this are used to construct this building, a lot of common structural designs these days. Now there's other things that aren't hollow sections like I-beams and C-beams that you might be familiar with, but the interesting thing about these is this is not typically a shape that's easy to extrude, especially not out of steel. So one of the ways of manufacturing something like this is you take a plate, you bend it, you slowly pass it through dies to form it, and you end up with two plates that have been bent around, or two edges of the plate that meet in the middle. And right down the middle, oh, not really down the middle there. Right down the middle, you have a weld seam. Now, if you have a weld seam there, it's just like this situation. We have bending, we have tension here, we have compression around the edges. But then imagine this is not a beam that's going across the ceiling. Imagine this is a column. If we have some compressive stress in most of this beam, and now we load it in compression as a column of a building, do you guys think that's going to change the stress at which it buckles? Hopefully that's what you guys would think. Because if you have some compression in there already, when you start adding more compression, you're not going to be able to tolerate as much load. So if you compare this to ideal case, if you take a sample of a beam that didn't have this weld and use that to test and design your structure, but how much stress you can take, you're going to find that in reality you can't take nearly that much stress. And people saw that when they started building buildings with these sort of sections. And that's what prompted a lot of the research that went initially into understanding the stress distribution, is trying to understand how that compressive stress develops and how you can predict then how that's going to affect the buckling strength. So we've talked a lot about stresses, a lot about practical distributions, a lot about complex distribution and drops. Now we're going to take it really, really basic to start. This, imagine, is the simplest model of residual stress. You got 3 bars. They're made of whatever material you want them to be. I'm going to say they're made of steel here just for simplicity. They can be round, they can be square. What's important is that however you're going to change their temperature, you're doing it in such a way that they're always at the same temperature. If you change one part of this bar, you're changing the whole bar. The whole bar changes temperature together. Everyone good with that? Now, these 2 blocks at the end are going to represent extremely rigid materials. If any part of this block moves in this direction, the whole block moves in that direction. It's got no flexing. It stays as a completely flat surface here. And the same up here. So this middle bar is going to be what we're going to look at. This is going to be, from this point on, the story of the middle bar in the 3-bar model. And all the complexity we see in the temperature distribution of welding, all of that is happening in this middle bar. So if you imagine this doesn't look a lot like a welded plate, but think about it for a second. When you weld, you've got some region away from your weld that is not affected by welding, at least not at the time you're worried about. You've got a big enough plate, you can imagine that near the weld, you've got temperature, you've got stress, but really far away, that temperature is not going to reach there. So the only thing that can happen to that region far away is some mechanical effects of your stress. So if you have stress near the weld, those mechanical effects can propagate differently than the thermal effects. Does that make sense to everyone? So this bar here, I've shown a typical temperature distribution, thermal history of a part of a weld. Now, this is not meant to represent the center line of the weld, the heat affected zone. This could be any part of the weld. Each part of the weld is going to have a different thermal history, but the story is going to be the same. If we imagine that this is really rigid, then it doesn't matter so much what's going on at each point. It's not going to be as affected by the points next to it as long as there's a really rigid structure, whereas each point in the weld wants to expand and contract. All the other points next to it don't want to let it expand and contract. Make sense to everyone as well? So we're going to look at what happens as you go and you start at a point where this middle bar is at some initial temperature T0. We're going to suddenly have heating, where we're going to reach up to some maximum temperature. And from that point, we're going to cool back to some temperature. And here, I've wrote the temperature as not as T0. In reality, it could be T0, it could not be T0. In reality, you're always going to have some amount of convection in your environment. It's always going to go back to the initial temperature. But what we're focusing on really here is we start at some temperature that's the same as the side blocks. We heat to some peak temperature, then we cool back down. And we want to look at what kind of stresses are going to develop and what kind of strain is going to develop as we go through that thermal cycle. So to start with, let's look at something similar but unrelated. This is a stress strain curve. And ignore this for now and just look at this curve here. Has everyone seen a stress strain curve? I hope so. You guys are all fourth year or graduate materials or mechanical or civil engineers, so this should be familiar. You start at some point where you have zero strain, zero stress. You increase linearly up to some point where you begin to yield. And then depending on your material, maybe you end up with a little bit increase. You have strain hardening, or if you have negligible strain hardening or you do an ideal situation, elastic, perfectly plastic, maybe you just kind of hang out of that yield stress until at some point you fail. Now for everything we do from this point, we're going to assume that we can use this elastic, perfectly plastic model. Now in reality, is this exactly what your material is going to behave like? No. But for a lot of cases we're dealing with, this is actually a pretty good approximate of our material behavior. So now let's look at how we try to explain this sort of situation, which is what we're all familiar with for stress strain, in the context of our middle bar for welding. So if you look here right now, this looks exactly the same as what we had before, except I've changed out what was epsilon total here for epsilon thermal. So typically when you take a stress strain curve of an object, you keep an object at a constant temperature and you pull on it. You stretch it, or you push on it, you compress it. And you're changing the total strain but leaving the thermal strain the same. We're doing something very similar in welding compared to, say, a compressive tensile test or a compressive test, where instead of adding some total strain in the form of motion, we're going to add some strain in the form of temperature, some thermal strain. But everything we expect to behave in the material should be the same. Does that make sense to everyone? Where if we're adding some amount of strain, instead of total strain, we're adding thermal strain. And we're going to look at how we can use this model of strain in a material to explain what's going on in welding. So this is the graph we're going to try to understand here. This is typically known as a Sato diagram, but we're going to look at this graph, and as we step through this graph, we're going to see how we get this kind of characteristic shape of stresses that develop during welding. So to start with, we're going to be in compression. Should make sense. We're heating something up. As we start adding thermal energy, if it's constrained, we're going to develop. We want to be longer than we are. We develop compressive strain. Does that make sense to everyone? You're with me so far? So if you imagine we start here with no thermal strain, room temperature, we add a little bit of temperature, a little bit of thermal strain, we're going to develop some compressive stress. So if we look at now a plot of elastic strain versus thermal strain, where elastic strain is, in our case, proportional to our elastic stress. As we move here on our tensile diagram, we've plotted it with absolute value of sigma, because this is typically what you see for compressive stress. It's the exact same, but now we're moving down into the compressive region. Hopefully you're all with me so far. Now, if we imagine we move a little bit further down, at some point in our compressive diagram, we're going to reach the yield stress. Now, at this point, we can imagine we've reached some equivalent strain to that yield stress. We're going to call the yield strain. Make sense? No questions so far? Now, let's see if I can plug in my mouse here so I get it. Perfect. So what happens next, looking at this graph, is hopefully what you guys imagine. Now, if we're elastically perfect plastic, we're going to start to yield. So although we keep adding more thermal strain, our elastic strain, which is here, and our stress can't change. This is what happens when you're yielding an elastic, perfectly plastic material. So we end up moving in a straight line. Now, we said that this is not a perfect representation of a real material, but we're going to see that this is fairly reasonable. Now, from this point on, this is typically where, if you have a stress strain curve, if you're doing material testing, this ends up being where you either end up pulling this to failure, or you take it back to room temperature. You take it, not room temperature, the initial zero stress level. But in welding, we could have any amount of thermal strain. We're going to go up to some very high peak temperature. We had a lot of thermal strain, or we go up to a lower peak temperature. So already, hopefully you can imagine, if this is our thermal strain, that's our peak temperature in welding. So you can imagine material that's really far away from the weld has a fairly low peak temperature, right? Which means you might not even get hot enough to yield. If you're really far from the weld, you might just go here and go back. You cool. You have no elastic stress. At least you would predict no elastic stress with this simple model. Now, alternatively, you might go up to some really high peak temperature. So high that you have all this extra strain that's beyond what was the strain where you started to yield. Now, if you imagine this strain is the same as this strain, what would we call that amount of strain in a stress strain curve? So this is our elastic strain. What would this be? Plastic strain. Right. So all of this strain we've exceeded our yield point by is the plastic strain. So now if we go back to, in this case, we return back to a zero stress state, it's because we've cooled a bit. So we now, to recap, we start at some initial temperature. We're going to heat up, developing strain elastically. At some point, we're going to reach a yield stress or yield strain, and we're going to keep at that constant level as we still develop more thermal strain. Then we hit our peak. Now, as we start to cool from our peak, we're going to be recovering that strain elastically. This is exactly what you see in a stress strain curve if you stop it at some plastic strain before failure and then allow your material to recover back to a zero stress state. But there's a problem here, because this is a zero stress state. So if you're in a typical stress strain test, this is where it ends. But this is not a zero temperature state. So in welding, we don't stop here, right? You can imagine we've heated to some point, we've reached a peak temperature, we've come back to some temperature, but we're still greater than the temperature we started at. So what's going to happen next? So we've now kind of reached the limit where we can describe what's going with a single stress strain curve. But what we can do is now start with a new stress strain curve. And this is the exact same as we had before, but now we flipped it. So instead of cooling, or instead of heating from an initial state, we're now going to cool, where this is no longer zero. This is whatever thermal strain we had here. We're going to start developing stress in the compressor, or in the tensile direction. Now this is probably the most complicated part of this, so I want to make sure everyone understands what's going on here. Do you see? We're trying to describe this pattern where we go beyond the initial point. So we have to flip our axis to start to understand what's going on. In this case, what's happening is we started off in compression, we reached some peak temperatures, and then as we cooled, we end up crossing what was our zero strain curve. And typically in a diagram like this, you can't go beyond your zero stress. You're either doing a compressive test or a tensile test. So we have to start a new test where we look at it, not from our zero state, but from this reference state, where as we cool back, we're cooling back towards what our zero state was. So in reality, you could imagine this zero axis, if you wanted to deal with zero thermal strain, would be somewhere over here. Does that make sense to everyone? I'm starting to see some glazed eyes. Now, what's interesting about this point is that as you cool back to our zero stress state, and then as we go beyond that zero stress state and cool, still moving back towards our initial temperature, we reach some point where we've now yielded again. So we yielded in compression upon heating. We kept heating, we developed all this plastic strain, all this thermal strain, and as we cool, we actually cool enough that we yield again in tension. So now if you imagine this is that bar, we've heated it up. We heat up to this point where we have all this thermal strain, all this plastic strain, and as we cool, once we get back to our initial length, we still have all this thermal strain and we still have all this compressive plastic strain. So we keep cooling, and then we reach a point where we've actually now, once we cool back to close to room temperature, we're now in tension. Does everyone see that? That's why we end up with tension in our weld, and it's not because of just thermal strain, it's because we had all of this extra strain that we couldn't accommodate, which became plastic strain. So you can imagine if you're at this point when you weld, this is kind of your critical point. Any temperature beyond this point, any thermal strain beyond this point, becomes plastic strain. And all of the plastic strain beyond this point eventually is going to lend it to stress. If we're here, when we return back along this path, we have zero stress. if we heat even a little bit beyond this point, when we return back along our constant elastic recovery line, we're going to have some amount of residual stress. So this temperature is going to be a really critical temperature for understanding stress, because this is going to be the boundary from where we have no stress to where we have tensile stress. And you can imagine that if we have really high temperatures, we have some plastic strain upon cooling. But really what we're interested in is this, any heating beyond this point, we're going to have some amount of plastic strain, some amount of residual stress. Now the other dashed line I've drawn here would be where you have yield level plastic strain, or yield level elastic strain, or yield level stress upon cooling. So really all of what we're worried about in residual stress is going to happen between these 2 points. Any heating beyond this point, the residual stress is pretty easy to predict, at least in the simple model. It's going to be yield level. It doesn't matter how much additional temperature you add beyond this point, our elastic strain, our stress is not going to change. So really what we're trying to understand is how wide is this point where we start developing elastic strain, or plastic strain? How wide is this point where we develop yield level stresses upon cooling? And if we know those two widths and we have an idea for what's going on between those two widths, we can predict the total residual stress we're going to have. So really, if we have those two critical points, and we look at them not as a thermal strain, but now as a temperature, where we've just, if we assume we have a constant coefficient of thermal expansion alpha, our thermal strain is going to be proportional to whatever that strain is at this point, divided by alpha. We can define two temperatures. And we're going to call this TC1 and TC2. And these are the two critical temperatures we worry about for residual stress. And we can see that if we look at this point, this thermal strain here is simply going to be equal to our yield strain. So we can divide our yield strain, which is going to just be our yield stress divided by elastic modulus. If we divide that by alpha, we can calculate what this temperature is. And we see for A36 structural steel, our yield stress is about 250 megapascals, elastic modulus about 210 gigapascals, and alpha is about, give or take, 1.2 times 10 to the negative 5 strain per degree Celsius. We can see that we'd have this at about 80 Kelvin. Now what do you guys think? Does that seem low, high? What do you think? In terms of welding, 80 degrees Kelvin seems low, but that's true. 80 degrees Kelvin is all the temperature change you need to start creating stress. So one of the things you can start to understand is why maybe this model where we ignore strain hardening, we ignore, in fact, we've ignored temperature dependence of yield stress, seems to be okay. If we're worried about everything over 80 degrees Kelvin, you can imagine that the region where we have stress is huge compared to the region of our weld, compared to our heat affected zone. So all of the really complex material changes, whether it's phase transformation, whether it's melting, whether it's the fact that your properties are changing at high temperatures, those are all going to happen, and they're all going to affect the stress you have in a region of your weld. But the total region you care about for stress is going to be so much larger that as a first approximation, you don't necessarily have to worry about those effects. And this is one of the really powerful things you can see with starting with this model. So 80 Kelvin, that's nothing. You imagine you're heating something with like a blowtorch. You can get it hotter than 80 Kelvin above room temperature.
So what you mean is 80 Kelvin is above room temperature?
Yes, sorry.
About 100 degrees C, not cryogenic, right?
Sorry, yes, this is a delta T. So this is 80 degrees above whatever our reference temperature is. So this is, if this is a thermal strain is going to be a reference to our zero strain state, which in this case would be room temperature, give or take 20 degrees C. Now you can imagine if you start with a preheat temperature of 100 degrees C, then this becomes 180 Kelvin. And the other interesting thing you see, this is our yield strain here, and this depends on our yield stress. So imagine we have one of those super high strength materials, it's 1,000 megapascals. This yield strain is going to become higher, and the temperature change we need to produce stress is going to become higher. So what do you guys think? If you have 1,000 megapascal steel, would you worry more about the effects of phase transformations? Yes? No? I would. If you imagine this is 4 times larger, this is 250 right now. If we go 4 times larger to 1,000 megapascals yield, this temperature change is going to become 4 times larger. Instead of 80 degrees, we're going to be worrying about 320 degrees above room temperature. 320 degrees above room temperature now becomes about half of the change above room temperature, 700 degrees, 780, to get phase transformation. So our residual stress region is going to get smaller. Does that make sense? You have a higher strength material. You need more thermal strain to produce yielding. So the region that you have thermal stresses becomes smaller. Now the stresses in that region are going to become larger because there's still yield magnitude and your material is stronger, so the stresses are higher, but the region where you have stresses is smaller. So all those complex effects of phase transformations of melting, they become more significant for higher strength materials because of that. Now, in practice, if we use this elastic perfectly plastic model, we actually don't even have to worry as much about what these temperatures are, because we're going to see it's the ratio that becomes really important. And it doesn't actually matter how strong your material is or what's going on. As long as you have this elastically perfectly plastic assumption, you're always going to have a ratio of this point to this point that's 2. And that's because if you imagine we have to get to 1 yield strain here, and here we have to get back to 0, back to a second yield strain, it takes twice as much temperature change. So the ratio between this peak temperature, where we have yield magnitude residual stresses, and this peak temperature, which divides a region of no residual stresses to some residual stresses, is always going to be about 2. Now, just to reiterate what we went over. So residual stress is going to be proportional to our residual elastic strain, which is where we are in this axis. Our residual elastic strain is proportional to the amount of plastic strain we have, how much we heat above this point. And our plastic strain is going to be proportional to our peak temperature. So we can end up with this simple expression where our stress equals elastic strain. Our elastic strain is going to equal to plastic strain. And our plastic strain is just how high we heat above this point. So if we know this temperature, about 80 degrees or 80 degrees above room temperature for structural steel, and we know our peak temperature distribution, we should be able to plot for every point in our weld how much our residual stress is going to be. So I think this would have been now probably a couple weeks back, but we talked about what that peak temperature distribution looks like in welding. So if you imagine you have a weld and you initially apply some heat, you've imagined this start at this point here. You've got all of your heat, or most of your heat is very close to the weld, right? And as you cool, you end up with what looks very much like a Gaussian distribution that just gets flatter and flatter. So this would be if you're looking at down the weld seam, right? You have sometime 0 where most of your heat is near the weld, then sometime a little bit later where some of the heat that was here is now spread wider, a little bit later some of the heat in the middle spread wider again, a little bit later it gets wider and wider. If you kind of trace down the side of those curves, you end up with this shape, which is actually an inverse shape, where this max temperature is proportional to 1 over the width. And that is the maximum temperature at each point in your weld. This is what we needed, right? So we need to know what the maximum temperature each point gets. We subtract that from this critical temperature, which we can calculate based on material properties. And from that, we get plastic strain. So if we look at that inverse shape here, and we pick out that delta Tc2, that critical temperature to get yield level plastic strain, or yield level residual stresses, that delta Tc1, we can convert that over to a graph that starts to look like what we see when we look at residual stresses, where everything within a peak temperature greater than this delta Tc2 is going to be yield level. And in this case, we've drawn it with the delta C, but this is typically very, very small. So imagine we drew this without any stress over here, and it was in a free plate. What's the problem with that? What's the problem in a plate, anything real, where you have a lot of stress in one spot and no balancing stresses anywhere else? Well, distortion is going to be reaction, but in reality, if you have unbalanced forces, you're going to have acceleration, right? It's not a static problem. We now got a dynamic problem. Our plate's going flying off into space because we have an unbalanced force. And in reality, that's not possible. So it's going to have some amount of distortion to develop some compressive stresses. What that means is if we have a plate here, and we have weld down the middle, and we have some amount of tensile stresses here, the plate's not just going to sit like that. As these stresses develop, we're going to have to develop some amount of shrinkage all across the whole plate which is going to shift the 0 point up a little bit to make our stress distribution look like that, because it has to be in equilibrium. Now, if we imagine our plates really big, then we don't really have to worry about this compressive stress because it's going to be very small. Now, in reality, we're always going to worry about that compressive stress. That's going to be what causes buckling. That's going to be what causes some of the deformations we worry about, is the reaction to this stress. But what we can say is when we're calculating how big this tensile stress is, we don't have to worry about that compressive stress because this length here is going to be much smaller than the yield magnitude. So we kind of do a little bit of a cheat there where we're going to ignore the compressive stress in order to calculate how big that plastic strain block is and how big those tensile stresses are. And then we'll use those tensile stresses again to calculate how big that compressive stress is. So we're not perfectly consistent, but we've taken what would be a really complicated problem where we have to deal with the fact that as this is developing plastic strain, it's also shrinking. And we've made it somewhat more manageable by saying we're going to ignore this initially. We're going to figure out what this stress is. Then we're going to apply that stress to a free plate, figure out how much it shrinks, and use that just to shift the stress up and down to make sure we're at equilibrium. And that ends up being what we'd call superposition. Has everyone heard of superposition before? Where you deal with one case, and then you superimpose some balancing stresses to make sure that it's in an equilibrium state. And that's what we can do here. And it makes it a lot easier of a problem to solve. Now, we don't have to do that. We could consider what's happening as these stresses are developing, as the plate's deforming while they develop. But believe me, that takes longer in a class to explain what's going on and all that. And it's really not going to make a big difference here. So if we look at this stress distribution, we can say, as we said, we have some maximum temperature. We've got some material properties here. This is exactly what we have in our notes from the thin fast regime 3 for the maximum temperature. But really, we don't have to worry so much about all this as we see this inverse shape. That shape here is going to be the same shape as our residual stress distribution. And if we look at this delta Tc1, that's going to be the bound of where we have this block. And delta Tc2 is going to be where we chop it off and we truncate it. And everything above that, we're going to say the stress doesn't increase any higher because we've hit yield. And if we now look at, we said our residual stress is proportional to our elastic strain is proportional to our plastic strain, and our plastic strain is proportional to our difference between our maximum temperature and our delta Tc1. Really what we're saying is we get this shape, and if we want to know the total residual stress, we just have to integrate this shape. Now, if this delta T max is proportional to 1 over y, that integral is hopefully something that maybe you guys all don't remember how to do, but you can imagine it's not that complicated. We've all integrated 1 over y before. Does anyone know what you get when you integrate 1 over y? Exactly. So if we go through and do that integral where we can ignore this delta c, we end up with this whole mess. Now, stay with me for a minute here. First thing, we end up with a logarithm. We end up with a logarithm and the ratio of our temperatures. Now, I told you that we're not going to have to worry about exactly what those temperatures are, but just the ratio. That's because when we integrate, we get log of one temperature minus log of the other temperature. We can make it the ratio of the temperatures. So although we know that this is about 80 degrees above room temperature and this is about 160 degrees above room temperature, really all we care about is the fact that those are 2. And if it's always approximately 2, we don't even have to worry about it. Now, the other thing we see here is all of those constants that were in our Tmax expression end up coming into play in our expression here. So we end up with some numbers in front that go with our ln. That's just a constant. That's going to be a number. That's not going to depend on anything. We don't have to worry about that. But what about what we see here? So this is our elastic modulus. That comes from the fact that to get stress from strain, we multiply by elastic modulus. This is our coefficient of thermal expansion. Once again, that comes, yep.
Just a quick question. Are those all logarithms? So is it ln t?
No, sorry, this is just logarithm of the first part. These are all just constants. So if you imagine when we do the integral, everything that doesn't depend on what we're integrating by, which is y, we can pull out up front. So it's just logarithm of the ratio. These are just extra groups on the end. So if we have the elastic modulus and we have our coefficient of thermal expansion, we can see those come from the fact that to get stress from elastic strain, we multiply by E. To get thermal strain or plastic strain from temperature, we multiply by alpha. So we have that E alpha. Now what about rho C? Rho C comes from the fact that we have this whole grouping here of Q over U rho C. So we have our heat input. In this case, we've written it explicitly as the effective heat input, because you can imagine if we start to deal with a practical problem of welding, which we want to get to, it's not going to be the total heat input that matters. It matters how much is actually getting into that plate. So this effective heat input, we're including whatever our thermal efficiency is. Because any heat that doesn't make it into the plate, we're not going to worry about from a stress perspective. From an efficiency perspective of welding, from how much power your machine's using, maybe it's important, but from a thermal strain perspective, if the heat doesn't make it into the plate, we're not going to worry about it. So we just care about the effective heat. And then this rho C is our volumetric specific heat capacity. So what's really powerful about this expression is that if we know the heat input, we know some material properties, we can calculate this integral of residual stress. And we can start to calculate how much we would expect something to bow, how much that compressive stress is going to be away from the weld, all sorts of really critical things for designing weldments, for designing structures that have welding. And all we need to know is our material properties and our heat input. Now there's something in here we don't need to know. Does anyone see what's not in here, which you might have expected to be in here? If you knew nothing about residual stresses, would you expect that maybe the yield stress of your material changes your stresses? I would. If you got a higher strength material, you got higher stresses, but it's not here. Why do you think that is?
Modulus there, does that account for it?
Different levels of steel are always going to have about the same modulus of elasticity. If you think back to our stress strain curve, the modulus is the slope of that curve. But how high it goes before it flattens out is going to be the strength. So even if we have an 1,000 megapascal steel, the modulus is still going to be right around 200 gigapascals. So we talked about this a little bit. If you imagine that we're looking at those yield temperatures, if we have a higher strength steel, that yield temperature is going to be higher. The region of material we're dealing with, which is this width here, is going to be smaller. So we have higher stresses because it's a higher strength material, yield strength is higher, but we have a smaller region. And what you see is that those two effects, when you actually go through and you do the integration, the two effects cancel. I think this is one of the most powerful things you can learn about residual stresses. If there's only one thing you remember from this class, it's that a stronger material does not necessarily have more deformation, more net residual stresses. The individual magnitude of the residual stresses, the peak value of this curve might be higher. But the integral and the total amount of stress you have to drive deformation, to drive stresses elsewhere, is not necessarily larger. Now I say not necessarily as a bit of a catch-all because we made some assumptions here. We assumed that we're elastically perfectly plastic. We didn't deal with phase transformations. We addressed that as we get to really high strength materials, some of those effects might start to come into play. Interestingly though, if you imagine you've got phase transformations, typically you actually end up expecting lower stresses in the region. So maybe high strength materials might actually have lower stresses. Now we're not going to worry about that and get into that, but if you imagine you're just doing a bunch of simulations where you're not really looking at the effect of your parameters, you wouldn't arrive at this conclusion. You could do a couple different materials where you have typical heat inputs for those materials, different widths of your weld, different widths of your stress region. And you might eventually, after tons and tons of experiments where you plot out a curve, you can develop an expression where you say, okay, yield stress doesn't really matter. We didn't have to do any simulations though. One integral you could have done after first year calculus, and you see that although the magnitude gets higher, the yield stress gets higher, each of these values individually gets higher, the ratio stays the same, and so we don't have higher residual net force. Does that make sense to everyone? So I've starred this equation. There's going to be 3 equations I star in these notes. Those are the 3 equations you're going to find on your formula sheet. So we talked a lot about the derivation of how to get to this value. At the end of the day, we're not going to ask you to reproduce that. Hopefully, if you go through these notes and you look at what we've done, you could. But what's really important is understanding how we got to this equation and what we can do with this equation. And if we plug in this typical value of 2, really, there's not a whole lot to worry about here. We've got some material properties and we've got a heat input. All that stuff you guys have seen before. What's our second equation? It's even simpler. We talked about how you have something that's been built up by welding. So in this case, we looked at a square section. What about an I-beam, where you had two flat steel plates and you made fillet welds across the bottom and the top and made it into a big section? This is actually from one of the first papers where people looked at this equation for what this force is, and I don't know if I mentioned, I think it was on the slide, but this would be called the tendon force. And people were worried about what this force was because if you have that tension force here, you have compressive force in the middle of this plate, and that affects the buckling strength of this column. And a really simple approximation is just to take that total net tension force, divide by, this ends up being the total area, where this is not just the width of the column, but it's the total width, the width of this plus the width of this plus the width of this, times the thickness. And you end up with your compressive stress. And that compressive stress you use to calculate the effective reduction in buckling strength of your material. Really powerful equation. Really simple to get to. All we need to know is some material properties or heat input, and we know the geometry of our material, and we can start to make really practical calculations about how our weld is going to affect what the strength of this would be in buckling compared to something that was fabricated not by welding. Now, if this wasn't simple enough, I'm going to give you guys an even simpler form. So if we look at the same materials I think have been on the formula sheet in the past for a heat transfer, and we look at what this value of coefficient thermal expansion is, what the elastic modulus is, what our volumetric coefficient or volumetric specific heat capacity is, we can collect all of this mess in front, including a 2, into a single constant. It's a material dependent constant. If you have the same material, this constant's always going to be the same. Now, there's a slight caveat to that where I say it's always going to be the same. We haven't considered preheat. We're not going to talk about preheat. You can imagine that this ratio could be affected by preheat, but as long as we're going to ignore preheat, we can always say that we have the same constant C1 for the material, because our material properties aren't going to change. Now, if you look at all these different constants, we went from structural steel to stainless steel to alloy steel to aluminum, titanium, copper, Inconel. We have some properties changing by a factor of 3, some properties changing by a factor of 2. Maybe the least changes in our specific heat capacity, but C1's always in about the same range. Now, this is more of a chemistry problem than a materials problem, but we see that we have E alpha here. Now, does anyone know what E is at a fundamental level? What is the elastic modulus?
Stiffness?
Right, it ends up being stretching of bonds. It's how stiff those bonds are. And what about coefficient thermal expansion? It's how much the average bond length increases when you start to add some energy to stretch those bonds. So if you imagine that you have stiffer bonds, then typically this is going to be smaller. Where if you have more flexible bonds, then this might be larger. So as this increases, this decreases. Now, there's a lot more chemistry and physics behind that relationship. This is just a rule of thumb. But if you understand it, you shouldn't be surprised that as this is higher or this is lower for some materials, in general, alpha is a little bit higher. And where this is higher, alpha is a little bit lower. So although we get a factor of 3 difference here and a factor of 2 difference here, we're not seeing a factor of 6 in our coefficient. We're really seeing maybe a 50% change all the way from alloy steel up to Inconel. This is something you're probably never going to arrive at if all you do is simulations. And because if you don't understand this relationship here, pulling out this understanding takes hundreds of tests. And each of these tests has to be typically full thermal mechanical modeling. You got to figure out how your geometry is influencing your weld. All of the effects that we can simplify here to really just pull out this fundamental understanding are really hard to get any other way. And that's, I think, one of the most powerful things about this equation. Now, a lot of people could study welding and probably never understand this because there's very few people who have really looked at understanding this tendon force this way. Now, I'm certainly not the first. A lot of people looked at it for buckling of columns. People have looked at it for other applications in structural construction. Some people have looked at it for predicting deformation of pipelines. But often in welding, you're going to hear me talk about this a lot if you ever talk to me about my research. People in welding, they go and weld. A lot of historical research in welding was people trying different things and looking what happened and plotting out trends. So this understanding, maybe a few people. This, you can find dozens of papers where people have done enough tests and realized, hang on, heat input matters. So there's tons of papers of people arguing back and forth about, well, I say arguing, but it's publishing and saying, I got a different result than this guy, and I got a different result than this guy. And it's all discussing what this C1 constant should be, without any of the understanding of where it comes from. It's just people doing tests with different heat input and seeing that in most cases they can draw a straight line if they plot it against heat input. And they put a coefficient on that straight line and they get a value. And interestingly enough, the values they get are all between a 0.15 and 0.25. Now, they're all doing the same material. That's all just for steel. And they're getting a variation from 0.15 to 0.25 because they're not all using the same geometry, they're not all measuring things perfectly, and they're not all using the same strength steel, so there might be some minor variations there. But they came up with this understanding. But if you look at those papers, you would probably rightly say, that's all done for steel. I have no hope in using this for aluminum. How could it be the same? It might be. If you understand where it comes from, you can understand, well, hang on, maybe this would work not too bad for aluminum. Maybe this would work well for additive manufacturing of titanium. Maybe this would work well for pipes that are clad with Inconel. And I think that's why this equation has so much more power than just a simulation. So, now we've done all the hard work, let's do an example. So this is very typical of what the question could be for this sort of calculation. And this is super, super easy. You don't have to, I hope you guys understand how we got to this equation, but to use it, you don't have to understand more than those people understood when they wrote those papers. There's some relationship between the force and heat input. So if we estimate the tendon force for a butt weld between two 0.135-inch 10 gauge A36 steel sheets, we have our equation for tendon force. We have our procedure for welding this with submerged arc. We see this last thickness corresponds to it. First step is going to be to calculate our effective heat input. Now our effective heat input is eta times voltage times current. So if we look for eta, it's not here, but does anyone know? Well, it's up here. Eta for submerged arc welding, give around 99%. When you have the flux on top of your weld, it helps kind of trap that heat. So you can argue, and you'll see different publications, but as a reasonable value, about 99% of the heat in submerged arc welding gets into the weld. Is that accurate with what was in the formula sheet? Now if we look at the voltage, 28 volts, the current, 675 amps, we can calculate our effective heat input, 18.7 thousand watts. Tendon force is as simple as plugging in that value and multiplying by our coefficient. Now we said it was A36. We go back, A36 structural steel, 0.22. 0.22 times 18.7 thousand watts. Divide by our travel speed here. Our travel speed in procedure handbook is given in inches per minute, so we convert inches to meters, seconds to minutes. Something interesting here. This is in watts. This ends up being in meters per second. What are the units of this coefficient? What do you think? There's a big hint right here. There's no units. It's unitless. So we have watts. Anyone know what watts is in its base system? Joules per second. So erase some of our pictures here. And we have joules per second divided by meters per second. Joules per meter. Joule? What is that? Anyone? Newton meter? Meter? Newtons. We get units of force. That's why this coefficient's dimensionless. If we look at the units of heat input and the units of force, they're the same. Now, completely different. Heat input is not a force. Heat input is the amount of energy you're putting in per unit length of weld. But if you're going to use it if you're going to use what ends up being not so much a scientific formula, this would be our scientific formula, but this is a practical formula. This is the kind of stuff that gets put into a code. This is really powerful because you don't actually care if this is an imperial measurement of heat input. This could be any units you want, and this coefficient doesn't change. It's always going to be 0.22. It doesn't care if you're dealing with the imperial system, the metric system. And I think that's one of the reasons that this equation and equations of this form became very popular, is because even though people were publishing in Japan or UK or America, they could all argue back and forth about what this coefficient was because it worked in all their systems. Even though some people were measuring heat input in calories per second, or calories per meter, I think, or no, calories per meter per second, whatever. If you look at old papers on welding, if you think kilojoules per inch is a bad unit, start dealing with calories and BTU, and you can start to understand why, even though in America kilojoules is not what they deal with, they've adopted it for welding because the alternative of calories or BTU is so much more unwieldy, it just didn't stick. So we calculate our tendon force, 81,000 newtons. It's a lot of force. I certainly wouldn't want someone to stand on my chest with 81,000 newtons of force. And that's all in a weld on 0.135 inches. That's 3.4 millimeter thick plate. I think that's amazing. That's a lot of force in a little tiny weld. Now, what if we give some thickness to those plates, or some width? If we say each of those plates are 250 millimeters wide, and we're going to neglect out-of-plane deformations, which essentially means this heat is distributed evenly through the thickness, which for a thin plate is a pretty reasonable assumption. Let's calculate the compressive stress. This is even easier. We take our tendon force, we divide by the total width and the thickness. Thickness, 3.4 millimeters, that's 0.135 inches. Total width, 250 on each side, is 500 millimeters. 47.6 megapascals. Now, that might be a lot, that might be not a lot. It depends on what you're dealing with. Now, this is A36 structural steel, so we said that's got 250 megapascals. So if we looked and we said we assumed that the yield stress, 250, was much, much larger than our compressive stress, about 5 times larger, I'd say that's not bad. If you imagine in practice 250 millimeters, that's a pretty thin plate. If we're building a large structure, this assumption is going to become pretty reasonable. Same thing if we're building a beam like this, and it's 250 millimeters on each side. We have 250 here, 250 here, 250 here, 250. We've now got 1,000 millimeters. We're twice as wide. This stress becomes half of that value just for the compressive stress, and our assumption gets even better. Same thing if we're dealing with even stronger materials. A36 is kind of one of the lowest strength structural steels you're going to encounter. It's only 250 megapascals. If you look at the plot from last class where we talked about 300W, 400W, 440W, all of those are significantly higher strength. And for a similar heat input, because this welding procedure doesn't say you can only use it for A36, you can use this for any structural grade, you can use this for any steel. Although, obviously there's some considerations if you start dealing with some exotic microalloyed steels. You can imagine that this becomes an even smaller amount relative to the yield strength, and our assumption gets pretty good. Any questions about that calculation? These are going to be the only examples of this sort of calculation you see, because this is new this year. You guys are the first ones who get to understand these formulas. So the guys next year are going to have a little bit easier because they'll be able to look at these examples, then they'll have some more examples from whatever we ask you. But for you guys, there's one more example, but this is going to be what you have to practice from. So if anyone's got any questions, now's a good time to ask them. No? I must be doing well. So last thing we're going to talk about here, bending distortion. So we talked about in this case, if we have a weld across the top, we're going to have some amount of shrinkage inwards, just like in a plate, that relates to the area. But we're also going to have some bending. And this is, who remembers what we talked about last class? Weld as a line. We talked about how much stress you could accommodate based on different modes, whether it was bending, whether it was shear, whether it was compression. This is very similar to that. But we're only going to worry about bending here, and we're going to worry about only the simplest cases where we're dealing with a hollow structural section like this. We're not going to worry about fillet welds and I-beams. We're not going to worry about any complex geometry, just square rectangular sections with a constant thickness, large and relative to their thickness, so it's nice and easy to calculate our moment of inertia. And we're going to be able to calculate, if we have a weld across the top, how much this is going to bend. So if you think all the way back to first year, Eng 130, we had formulas like this for bending of beams. Now, one thing that's maybe not intuitive at first, but I'm going to hope to explain here in the next couple minutes, is this formula for constant moment. This is what we want to use for the weld on a beam. So if you think of our tendon force, it's not like a lot of forces you encounter. It's an internal force. It's in the weld. If you cut your beam in half, the force is still there. Each half still has a tendon force. It's not a force per unit length. It's just a force, just newtons. So it's inherent to each unit of weld has that force that develops. The only analogy I can think of that some of you might be familiar with is you imagine, like, does anyone know how they make pre-stressed concrete? Anyone take any civil construction? You take a piece of rebar, you stretch it, you pour the concrete, you let it cool, then you release the rebar. That rebar pulls back to its original shape where it wants to and puts compressive stress as all. If you cut that concrete through the rebar, you still have stress in each piece of concrete because the rebar is inducing internal stresses. That's what a weld is doing. So if you look at, there's no thing for a force in each unit of weld where you have a constant force throughout your length, but we have a constant moment, which if we have a force on the top and that's some distance above our neutral axis, that's going to cause a constant moment throughout our beam. So this case of having a moment applied at each end where then you have a constant moment throughout the length of your beam, this is going to be the equations we want to use to understand tendon force. Does that make sense to everyone? A little bit? Getting near the end of class, people are just holding on. So if we take a look at the equation we have here for the maximum deflection, which is going to be measured like this. If you take your beam, you bend it, you flip it over so each end is touching, you measure your deflection in the middle, this delta. Delta is going to be equal to ml squared over 8EI, where L squared is the length of your beam, m is the magnitude of that moment, E is your elastic modulus, and I is the moment of inertia, measured about the axis, which is perpendicular to the weld. So if that moment is just the tendon force times this distance above the neutral axis, we can call that h. Then we can take ml squared and get our third and final formula we have to worry about from today's lecture, which is just really simple formula for what this distortion is, what this bending you get from welding across the top of one of these beams. So for our last example, we're going to start with the same thing, but we're going to now explain and we're going to calculate what that distortion would be. So if we look at what is the deflection each end of a 1 meter long 8 by 2 by 1/8 hollow structural steel section. So if you look at and you Google hollow structural steel sections, you get dimensions like this. And basically 8 is the width, 2 is the height, and 1/8 is the thickness. 3 dimensions is all it takes to describe the shape of this. And I've pulled one page of a handbook where we've got our 8 by 2 by 1/8. You can imagine this goes, there's only 4 on this page, but these come in all sorts of shapes and sizes. There's huge, huge ones that are 14 or 16 inches across, and there's small ones that are only 2 inches by 2 inches with really thin walls. But if you end up with a handbook like this, and we look back at, well, first step, we want to calculate our heat input. So let's start there. This is exactly the same as we did before, except here we've even given you all the parameters in the right units. So current of 140 amps, voltage of 18 volts, travel speed 6 millimeters per second, and we're going to look at GMAW with argon shielding gas, so efficiency of about 0.7. 0.7 times 18 times 140, 1764 watts. We didn't say here, actually I meant to say here, but we're going to consider this as a structural steel. Typically these hollow structural sections are made of a structural grade of steel. Hopefully that shouldn't be surprising because HSS is in the name. This should have said, assume it's A36. So 0.22 times 1764 over 6 millimeters per second. Now we have a force. This is where the other question ended. Very simple. calculate a heat input, pull your coefficient, divide your, or calculate a power, divide your power by travel speed to get a heat input, and calculate a force. Now we're going to go one step further. So if we want to apply this equation, we have a force, we have a length that was given in the question, we need H, we need I, and we have E. Elastic modulus for steel is about 200, 210 gigapascals. So if we look at our section, 8 by 2 by 1/8, we have all these properties across the bottom here. Now one thing that's a little bit interesting, if you look at the wall thickness, 0.116. It's not 1/8. It's a little bit less than 1/8. That's typical. You start to find that when you figure out something that's nominally 8 by 2 by 1/8 is never going to be exactly 1/8. It's not going to cause us a problem here. We don't need to know the thickness in our formula. We just need to know that distance between the neutral axis and the top and our section, or our moment of inertia I. Now, moment of inertia I, that's right here, 1.72. We don't see anything described as that distance there. So anyone guess how we can get that distance? Anyone know what this section modulus is? SY? Typically, that's going to be the distance to this mid of this top section from the neutral axis divided by the moment of inertia. So that's really actually H over I is this SY. Now, in this case, we see that I over SY, they're the same, so that means that this distance is 1. Now, nominally, we were 8 inches wide by 2 inches tall. If we go from 1 inch from the neutral axis to the middle, shouldn't be that surprising that we're right around 1 because it was nominally 2 inches. You could also just take this section modulus and say H over I equals 1.72. So if we pull out those numbers, here I calculated the D just so you guys can see that it's not exactly 1/8 of an inch, 3.2 millimeters, but H, 1 inch, 25.4 millimeters, I, 1.72 times 10 to the 4. We end up with a large number in millimeters to the 4th. Plug in our tendon force, 65 times 10 to the 3 newtons, L squared, H, 8, E, 210 gigapascals, and I, we get a distortion, 1.37 millimeters. Does that make sense? Does anyone, what do you guys think? Seems reasonable? You think that people are manufacturing these beams all the time, using very similar approaches to this, meter long, 1.37 millimeters? That seems all right. You imagine if this was, 10 millimeters, every time you see a section like this, it's going to be completely bowed. People wouldn't be able to use them. They wouldn't manufacture them this way if it was 10 millimeters. They'd be using other techniques. They'd have to control the heat input. They'd have to bend it back. 1.37 millimeters over a meter length seems reasonable. You can imagine if you're dealing with that in construction, that's probably something that, although is not perfect, you can tolerate. You can account for that. Now the last thing we're going to do here is just take a quick look at how we can take this formula and make it almost as simple as we saw before. So this is our formula for, almost as simple as we looked at when we looked at our practical formula for tendon force. So if we go all the way back here, we had a complicated formula and something nice and practical, something people could use in industry. Now, this is something from 1966 in Design of Welded Structures. I think I brought this book here when I showed you guys the Lincoln Handbook. I had all those other books with me. This is one of those books, and this is a practical formula for computing distortion in all sorts of different shapes, which has the area of your weld, D, which is what they've called, what we called H, L squared, which is the length of your member, and I, which is the moment of inertia. And they get this factor of 0.005 in front. This is a super practical formula, and they didn't come up with this through, at least they have no evidence to suggest they came up with this through analysis. It looks like this was just, they did a bunch of welds, they measured them, and a little bit of understanding about how beam bending works, they came up with this coefficient in front. But we can do something similar with our equation. So we have this Ft, but we know for structural steel that's about 0.22 times our Q effective over U. And our elastic modulus is about 210 gigapascals, 210 times 10 to the 3 megapascals. Now the other thing they had is they had a weld area instead of a heat input. Now, we talked about this a little bit at the beginning of class, but this came from our lecture on metal deposition. For a given volume of weld deposited, there's an approximate relation to heat input, about 60 joules per millimeter cubed. Now, this is nominal, because that's how this expression was derived. This is effective. So we also have to consider the ratio of effective to nominal, which is our thermal efficiency, and we get about 0.7. That's for GMAW with argon. Now, were they using GMAW with argon? They don't say, but give or take, in that ballpark would be not too unreasonable for any GMAW or stick process. I think GMAW with argon seems reasonable because you imagine if you're manufacturing long beams, even in the 60s, you don't want to use stick welding. That's going to take you all day if you've got stick welders swapping electrodes. You imagine using a wire-fed process, probably going for high efficiency, so spray transfer, getting a lot of material down there, so you want to have some argon. But you plug those numbers in, we get 5.5 times 10 to the negative 3. So we get 0.0055, they had 0.005. I think that's pretty incredible that just plugging in numbers, we didn't have to do any experiments. We could end up with very close to a really practical equation that people have known in this form since the 60s, but they could never get to this for any other material because they just did this from experiments. So you guys now know everything that people knew when they were, or at least everything people had about distortion when they were building stuff in the 60s, but hopefully you know so much more because you also know where it came from. So that's all we have for slides today. Does anyone have any questions? So these slides, yep.
Is this formula can be used for any already existing data that we have?
So this formula here or our formula? So in practice, they've used it for a bunch of different cases and they give the data here so we can compare it to these. There's some assumptions we explicitly said we made in our formula, one of which was we're assuming that we're using the 2D fast solution for temperature. If we have a structure where our heat distribution is going to be a small amount of the thickness, so you imagine even in this situation, we wouldn't expect our formula to be perfect because if we're putting heat in here, depending on how thick this web is, this is not quite like the butt weld we looked at in our temperature distribution. This is closer, but still not perfect. So there's some approximation. The difference between this and our formula is we know what assumptions we made, so we can make some reasonable decisions about which data might fit it and which data might not fit it. But if we're looking at distortion of a section like this, should work. If people do publish distortions of sections like this. If you imagine long seam welding of a pipe, that would work. It's no different than a hollow structural section. You could actually even use this approach for circumferential welding of a pipe, which is what I do a lot of my research is related to. There's a little bit of extra considerations when you're looking at welding around the outside of a pipe. It's not bending in the same way, but if you understand how that bends compared to how a beam bends, up to the tendon force, everything's the same, and then it's just how you predict this delta. You're not using the equation for beam, you're using the equation for bending on the end of a pipe. Does that kind of answer your question? So these slides should be up on eClass. Did anyone get them before class? No? If you guys can't see them on eClass, send me an email. They should be there under the folder of residual stress right after the notes from last class.